So I want to start by thanking Stephanie, Christopher, and all the other organizers for organizing this really excellent and also very timely workshop. So I very much enjoyed it so far. So what this talk is about really is on designing neural models that can carry out algorithmic tasks efficiently and effectively. Okay, so it kind of fits very well with the theme, which is graph learning meets theoretical computer science. So let me actually start with one step back. So algorithms, we all know that as systematic procedures to solve problems has been with us for a very long time, since ancient time, like the Euclid's procedure of calculating greatest common divisor, that's an algorithmic procedure. Okay. Now, about 60, 70 years ago, this computation power brought to us by the modern computers really has led to a paradigm shift in how we think about and design algorithms. So for example, nowadays when we talk about algorithm, very often we refer to computational algorithm, computer algorithms. Okay. And now, of course, in recent years, with amazing, impressive power showcased by modern AI, it's also natural to ask whether by fusing the modern AI and the power of data, whether this can lead to yet another revolution in how we design algorithms. Okay. So in particular, we have this huge literature in classical algorithm design in theoretical computer science, and have given us many very beautiful algorithm frameworks, deep insights about the mathematical structure behind the problem, the task at hand, many approximation algorithm frameworks and so on that has theoretical guarantees in terms of time complexity, approximation guarantee, etc. Okay. On the other hand, many of those theoretically beautiful sound algorithms, even when they have polynomial time complexity, they don't often translate to practical algorithms. We don't use them in practice because they're still very high, the time complexity. And also it's very hard to design algorithms that it's very hard to articulate what could be the pattern behind the data and leverage that pattern to design your algorithm, okay? Now, at the same time, we have seen this amazing power of AI in learning from data, in capturing the hidden structure in data and further using that to help with prediction tasks. Okay. However, there are many theoretical questions remain open, including that does a learned model really generalize, especially in the out of a distribution setup? And we heard this really nice bootcamp this morning talking about out of distribution generalization as well. And even simpler questions sometimes that if I give you a specific architecture, does that architecture have the capacity to implement or approximate certain algorithms with guarantees? Okay. So one of the themes that I've been really interested in recent years is how can we combine algorithm ideas and insights with neural network models to develop more powerful frameworks that can hopefully also learn from and adapt to data to solve potentially hard problems at hand, including NP-hard problems. So in this talk, what I'm going to focus on is this size generalization of a neural model issue, which has already been mentioned a couple of times yesterday in Xi's lightning talk and this morning as well. Okay. So basically, can a neural model with bounded complexity in terms of its number of parameters? Okay. You can run this neural model many, many times, depends on M, but the model complexity, the number of parameters is fixed, can extrapolate out of distribution generalizes to inputs of arbitrary and potentially unseen size. Okay. So I want to just remark that this size generalization, or sometimes in the transformer in large language model literature also sometimes you see this length generalization, because there they treat the input as sequence. Okay? But if I treat this as a set, then cardinality or size is more suitable. So this is a fundamental property of classical algorithms. So if I have a sorting algorithm, it cannot say that it only sorts things sequence of length at most 10,000. It has to sort any input size. And it's ideal if you want to have neural algorithm modules, but it's highly challenging. And so just think that if I give you an ideal neural sorting model, okay, you probably train this model on sequences of bounded size, but then you hope that when you apply it to future sequences, you hope to be able to get some guarantee that this model works for any size. Okay, so this is fundamentally out of distribution because your training data, without making further assumptions, this is never going to be the same distribution as the testing data. Okay, so the space is also infinite dimensional in some sense. And this is even more crucial if you want to solve hard problem. So if you have hard, say NP hard problem, say traveling salesman problem, then most likely that during the training, you cannot afford to have a lot of large instances that you already know the solution. You're probably going to train this on problem instance of small size, but then later you hope to be able to apply your model to larger instance of larger sizes, okay? And as I said, that in the classical machine learning setting, usually we assume that the training set and test coming from the same data distribution. And of course that there also, we heard from this workshop, there are many very interesting work on the transferability across sizes, including that for inputs coming from, say, graphs sampled from graph functions or coming from manifold structure. And there's also this really nice presentation yesterday by Yusu on this, towards a new theory of size generalization. In what case they try to model that in the worst case, in what case can we say that this, by the interplay between the model, the architecture, and the problem allow you to have generalizable solutions. Okay? But in general, this is a hopeless task, and without assumptions that it's probably not achievable. Okay? So the main theme of this talk is that there is a way that you can hope to facilitate this, this kind of a generalization by aligning your neural model with some algorithm structures. It's like that you're giving your neural model some algorithm scaffolding, hope it to facilitate to learn the parts more, target only learn the useful parts. Okay, so help to learn the procedure instead of fitting the data. Okay, so loosely we call this algorithm alignment. Its term is not made by us. I'm going to refer to Stephanie's paper later very soon. So the first part, which is going to be very brief, I'm going to mention one of the theoretical justification of that this kind of alignment indeed can lead to provable benefits in terms of the out of distribution generalization, okay? Then I'm going to spend most of the time talking about designing practical neural models to solve a family of geometric optimization problems, the problem of the flavor, like fitting shapes, okay? And to see that in practice, this is also bring benefits. Okay. And there's some earlier work along this, that how we use this algorithm alignment ideas to design neural models. I put some reference here. I'll be happy to talk about them if you're interested in particular. This piece of work is on an NP hard problem, the minimal Steiner tree problem. All right, so now we all know that mathematically a neural network essentially is a way to parameterize a function, a continuous function from input domain to the output domain. Okay. And we also know that the model performance are affected by the interplay of your neural architecture and the type of data that you handle. So for example, for image data, we have CNN. For graph data, we heard so much about the graph learning models that are very effective on this specific type of, more effective on this specific type of data. And we also know that the model effectiveness is also affected by the interplay of the neural architecture and the task structure. Okay. So we saw this picture yesterday and also this morning already. So this is a picture taken from one of Stephanie's earlier paper, which shows that when your neural model has certain alignment with some algorithm structure that make it easier to learn that procedure. So for example, here, suppose we want to solve the shortest path, graph shortest path, using the classical Bellman-Ford procedure. Bellman-Ford is very easy. You just keep doing a bunch of iteration. At each iteration, what you do is that every node simply take the current shortest path estimate from my neighbors, and then each neighbor send their shortest path estimate to me plus the edge weights, and I decide, do I get a better estimate? If I do, I update. That's it. Okay. So from the algorithm speaking, you have this nested for loop, and the inside, this is you just each node update from the neighbors. Okay. So this since we are all very familiar with the graph neural network, we already see that this aligns very well with the graph neural network, where you can think that the outer loop is just the number of iterations in your GNN, and then the inner loop is essentially every node is using shareable ways to carry out some operation at the simultaneously, and this operation essentially is basically aggregating information from the neighbors. Okay, so this means that when you train a graph neural network to simulate the Bellman-Ford, you don't really need to do this. You can focus on this inner part, which makes this much simpler to train and learn. Okay, so that's the intuition. Okay, and the goal is that by giving, you also don't want to do this so much. You don't want to completely dictate what your neural network is doing. You really just want to give some high-level kind of nudge, some scaffolding for your neural approaches, so to make it easier to learn, make the learning more efficient. Okay, so you want to have this structural resemblance of your neural architecture with some algorithm structure. Okay. Now, I should say that I cannot give you a better definition of algorithm alignment. In the original paper in Stephanie's group, they did give one definition from the pack learning perspective, but I think in general, a more general definition is still lacking, in particular since this is really should handle this out of distribution setting. Okay. But empirically, people have observed that when your neural architecture has some resemblance, that with certain type of algorithm tasks that indeed facilitate. For example, in transformer, there's this nice paper on that length generalization, where they argue that transformer is more effective when the task at hand can be written using this RASP programming language in a simple manner. Okay, and in the graph learning community, of course, where they seen that people observe that the graph neural network intuitively dynamic programmer, and there's also more recent work on graph neural network can also align with certain gradient descent for SDP. That's also from, I think, Stephanie's group. But we don't yet have a more precise, we haven't yet articulated the precise benefit that this algorithm alignment can bring us. Okay. So in the first part, I'm just going to very briefly tell you some of the recent results. This is a joint work with my students, Riley Nerem, Samantha Chen, and my colleague, Sanjoy Dasgupta, on that in a very specific case where we do, when you have this alignment, you do see the benefit in terms of out of a distribution generalization. Okay, and in particular, this is going to be for solving the shortest path problem using the Bellman-Ford procedure. We already seen the alignment previously. Okay, so I'm going to present the precise statement very soon. But roughly speaking, this is saying that if you train your this graph neural network with a specific loss, if you train that with loss sufficiently low, then you get the guarantee that what you get has to extrapolate to arbitrary graph with arbitrary edge weights. Okay, so I would say that this is perhaps the first type of results of this kind. There's also a lot of work actually focusing on the computational limitation of a neural model, especially transformers, that recent years we've seen a lot of very interesting work in that direction. It's of orthogonal flavor. Okay. So just to tell you the results, and let me start with this very simple case also just to explain the intuition behind. So here, we're going to consider now, this is almost the standard GNN, but instead of the sum aggregation, I'm going to use the min, which is opposite of max. So that you can think this is just I'm using max aggregation. Okay, this aligns well with Bellman-Ford. Okay, and I'm also going right now. Let's consider super small GNN, where the number of neurons that you have essentially are just the smallest general GNN necessary to implement a Bellman-Ford. Okay, so for this very particular case, okay, and let's also only try to approximate the one-step Bellman-Ford. Namely, I just want you give me a graph with some initial distance estimation. The output should be after one-step Bellman-Ford. What's the estimate? Okay, so in this case, it turned out that there exist just 8 graphs there of this form. So 4 of them looks like this, 4 of them looks like this, such that if the training loss of this small GNN over this 8 graph is sufficiently low, is at most epsilon, then your weights has to satisfy this equation inequalities. Okay? And if this equal to 0 instead of epsilon, then you basically get one of the ways to implement Bellman-Ford. There are infinite ways to implement Bellman-Ford using this model, but then if this equal to 0, you get one implementation of Bellman-Ford. Okay? So basically, essentially, you approximately implement Bellman-Ford if your loss is sufficiently small. Okay? And why is this happening? And intuitively, what happens is that because of this very obvious resemblance between this architecture and the Bellman-Ford, if I ignore this, so here activation ReLU, if I ignore the ReLU, this almost just become linear equations. So you essentially design this graph to force you to solve a system of equations, to force that the solution of those system of equations falls within this good range. Okay, so that's the intuition. And this comes because you have this nice alignment between your architecture and the procedure that you're looking at. Okay, but of course, this small model is not very useful. Yes?
So here you do not assume any, say, numerical precision of the weights. So W are all like real numbers.
These are all real numbers, and the statement really just say, I don't care how you train this. If in the end, your loss is at most epsilon, this is what you have. Yeah.
Right. Because I'm just wondering, because I think some of the results that you cited in the previous slide on transformers, they prove negative results essentially due to you have a limited precision.
Right, right. So those are a little bit different, especially a lot of those results are actually lower bounds. Where the machine precision comes into picture. That's why you always see the log n, just because, yeah.
Right, I see. Thank you.
Now, but in general, of course, you don't have this very limited, very narrow GNN. You could have an arbitrary graph neural network still using min aggregation, okay? It can be arbitrary depth, arbitrary width, the latent dimension, okay? So in this case, now there's just too many ways to go wrong. And in fact, both the results that from this paper, I think this is one of Hagai's paper, and also it was mentioned yesterday in Yusu's lightning talk that in general, you have the negative results. Namely, if you just fix your training set and your model is large enough, then you can fix the training set perfectly, but then arbitrarily run for the test set, okay? So here, it turned out that the way that you can save from this is through regularization. Namely, the loss that I'm going to train my model is not just, in addition to the standard loss, the error, you also added the sparsity of your model. Okay, so we use L0 here. Okay, and now with this L0 sparsity regularized loss, you get a similar results where, again, if your training loss now is sufficiently low, there's more conditions, which I'm not going to get into that. But as long as the training loss is sufficiently small, then you have to be close to one of the correct sparse solution to implement the Bellman-Ford, which means that now you can have arbitrary graph of arbitrary degree, arbitrary edge weights, and you get guaranteed Bellman-Ford. Okay, and in fact, your training set doesn't have to. This is the same 8 graph that I was talking about, but your training set can be any superset of that. We just need this 8 graph there to have anchored to solve your system of equations. Okay, you have additional graphs. Although when you have additional graphs, when your training set become larger, this the range where the condition on your training loss also become stronger and stronger, become smaller and smaller. Okay. And you can also, you don't have to limit yourself to just one step Bellman-Ford. You can go with a k-step Bellman-Ford. But by the way, to solve the graph shortest path, one step is sufficient, because once you train one step with bounded loss, you can just recurrently apply this many times to compute the shortest path. Okay. Nevertheless, you can do the k-step directly, and here your training set becomes, instead of 8, you have order of k, but they're still very, we give them explicitly, you know what's the form of this graph. They're still all very simple. Each graph has only, so the training graph has only size k, but it works for a graph of arbitrary size and complexity. So that's the first part. Now, I should say that it is the result itself is only for this Bellman-Ford. However, I think this is the first time, at least, I mean, it bothered me for a long time that we talk about algorithm alignment. It seems empirically we do see better results. But why? I think this is at least give a theoretical justification that this can lead to provable out of distribution generalization. Yes?
So for these examples, it's better to train this model with small graphs than large graphs.
So we actually, yes. So I didn't show empirical results. We also have an empirical result to match all the theoretical results. So what's interesting is that when I train the neural network is over-parameterized, okay? If I only use this theoretical graphs, or I use a much bigger training set, including many other arbitrary graphs, okay? What happens is that the larger training set essentially also converged, but it takes much longer from optimization perspective to. So it seems that since it's here, you know the problem that in general, when we do machine learning, we don't exactly know what's the problem, what's the task, right? Since here you know that using this specific training set is more beneficial. Yeah. Note that this doesn't mean that I have to only do Bellman-Ford. I think even this is useful in practice. Imagine that in practice, probably the decision that your model is making is based on some implicit shortest path. You don't know how it's computed. You don't know how maybe the weights is some transformation of your nodes and the edge weights. Okay, so here, as long as you give the training signal to be the shortest path, it means that you can potentially extrapolate. Yes?
So what happens if you replace the min by summation?
Right, so I think one might be able to, because I mean, given this universal approximation power, that the max function can also be approximated by when you use the sum of some polynomial, and maybe you also need the polynomial outside, you might be able to get some weaker results, but max is just make everything so much easier, yeah.
Could you maybe train these apart, like separately, like you do like first some alignment to kind of import the min and then plug it in? I don't know.
Yeah, that's possible, I guess. Yeah, specifically train for that, yeah. All right, so now I want to give you now more practical problem. There's no theoretical guarantee. However, now I'm going to show you the practical performance on designing neural models to solve certain family of problems where the architecture will be inspired by some algorithm framework. So the family of problem is this so-called geometric shape fitting problem. So it's very classical in computational geometry, where the problems of the following flavor. You're given a set of points in d-dimensional Euclidean space. I'm going to use two-dimensional example. And there's also some target shape, say balls. Okay? And now you want to find the optimal shape covering this set of points. So for example, if the target shape is balls, then this is so-called the minimal. This is a very well-known problem, the minimal enclosing ball problem. You're looking for the smallest radius ball that cover all the points. Okay? You can also have the min width annulus that you try to optimize the width of this annulus that covers the set of points. Okay? So the whole range of optimization problems of this flavor. Okay? And I want to design a efficient neural model that can handle the input of arbitrary size and also has the capacity of solve them approximately. Okay. And note that with a neural model to solve this problem, compared to classical algorithm, one benefit is that this is also differentiable, that potentially you can integrate this module with other neural machine learning pipelines. Okay, because this thing now is differentiable. You can, for example, add this into part of your loss function if your final thing is trying to optimize certain quantity related to this. All right, so let's just look at this really simple minimal enclosing ball as an example. This problem itself is not hard. They're very efficient algorithm, but I want to use this one just to explain the ideas behind. Okay. So here, we're given a set of points, and we're looking for, you want to return the radius of the smallest enclosing ball covering all the points. Okay. And now, if you take 1 minute to think about how would you solve this, how would you design a neural network to solve this problem, and it's very likely that you might come up with something like this. So our input now for this set of d-dimensional points, we can represent as a sequence of d-dimensional objects here, and then feed it into either a transformer or something called a sum former. Essentially, this is a sequence-to-sequence permutation equivariant block. Okay, you have a whole bunch of such blocks run for a few blocks, and then you do a final readout to return the final estimate to the radius. Okay, so this is a very sensible way to have a neural model to solve this problem. Okay, and this individual block, you can use transformers, which is a sequence-to-sequence permutation equivariant. You can also use the so-called sum former, which is really just a slight generalization of the deep set. Okay, so the sum former, so transformer is a quadratic time complexity because of the self-attention. The sum former, basically, your input is n points in d dimensions. Output is, say, n points in another dimension, k dimensions. And each of the output, so first you basically you get a global information of all the entries. You transform each of the input by phi, and then sum it up, just like in deep set. Okay? Then you pass this global information to each individual at the ith entry. So each one take its own value under the global information and then compute the final entry. So this is also similar to in graph neural network, you have virtual nodes where the virtual nodes aggregate everybody and then send back to everyone. Okay, so that's more powerful than just has some global information encoded through the virtual node. Okay, but this is a linear time complexity because you are just aggregating this once and then send back to everyone. So compared to transformer, this is more efficient. So if we do this, so here is some of the results for the minimal enclosing ball. So here the model is trained over a whole bunch of point sets where each point set has about 200 points. Okay, and the test point sets, each point set has between 50 to 3,000 points. Okay, so the blue one is the sum former version, and this one is the transformer version. Okay, so as you see that once you go out of distribution, the error become larger. Okay, and the performance of these two models are kind of similar. I mean, maybe sum former is a little better than transformer, but it's very similar. Okay, but from the running time perspective, sum former is linear. It almost looks flat because of it just grow it's still linear. But transformer is quadratic, so it's more expensive. Okay. So when look at this, one might ask, is this the best we can do? I mean, and also we do see this that our error goes up as I run on much larger point sets, okay? And also, is sum former sufficient? Do I really need to use the more expensive transformer, for example, for this kind of problems? Okay. And for that, I'm going to show that actually there's a way to design better, still very simple, almost as simple as this model that I show you, but then going to work much better than both of this, okay, with a little bit of algorithm alignment. And, but for that, let me first tell you a very simple approximation algorithm already known in computational geometry to solve this minimal enclosing ball problem. The idea is beautiful. So this is, I'll give the reference in a minute. So let's say that you give me a set of points that I want to compute the minimal enclosing ball. Okay. What we do is at first, I'm going to compute a subset of the points, Q. The subset is the so-called epsilon kernel, where some error parameter epsilon. So now the cardinality of the subset is much smaller. I'm only going to solve this problem on this much smaller point set Q. Okay, so that's a green circle here. Once I solve this, I just return this. And this is going to guarantee to be give you an approximate solution of the optimal minimal enclosing ball. Okay, of course, it lies in how this epsilon kernel is defined. Okay, so basically, you don't need to solve this for all the point sets. You just take a subset of the point sets and then solve it over there. Okay, so what is this epsilon kernel? The epsilon kernel essentially simply approximates the so-called directional widths. So, this set of points, if I take any direction, I can look at the projection of the points onto that direction. I can look at the width of that interval. Okay, that's called a directional width. And epsilon kernel is a subset of points Q such that no matter which direction you're looking at, my smaller set of points always approximate this directional width for you within epsilon accuracy. Okay, so the epsilon approximates the directional width. Okay, so the idea has been in the community for a little bit, but in the end, it was unified in this really beautiful paper by Agawa et al. You can check it out. And so now, why is that useful? It turned out that the radius of the minimal enclosing ball is one example of the so-called extent measure. A measure is that this is different from statistical science measure. This is just that you give me a set of points, I return you a real value. Okay, that satisfies some condition. You can think that all the quantities that we try to optimize for the shape fitting problem, those are all some sort of extent measure. Like I try to optimize the radius of the smallest radius, the radius of an enclosing ball, or the width of an annulus that covering set of points. Those radius are all one of this extent measure. Okay, so Agua et al. They showed that for any nice measure called a faithful measure, for which this radius of minimal enclosing ball is an example, if you have a epsilon kernel, then the solution from the epsilon kernel will guarantee to approximate the solution of the original point sets, okay, for those kind of measure. Okay. And again, the example of faithful measure includes like a min volume bounding box, volume of the convex hull, and all of this. And you can see here that all this quantity kind of related to the convex hull, convex body, smallest convex body enclosing the set of points. That's why this epsilon kernel intuitively works. Okay. All right. So what this suggests is that for this kind of faithful extent measures, if I can compute the epsilon kernel, then the algorithm to approximate this measure is simply time to compute the epsilon kernel plus the time to compute this quantity only over the extent, the epsilon kernel. Okay? And you can also construct the epsilon kernel very easily. This is not the best algorithm I'm describing here, but it's very easy to align with neural network. So the way you do this is that when in d-dimensional space, I simply take the d-dimensional unit ball, unit sphere. So I look at all unit vector in d-dimensional space. I take a cover of the unit sphere. So basically, now any other direction will be within epsilon distance to one of my covering direction. Okay. So the size of that only depends on epsilon and d. Okay. Then for each of this direction in your cover, you simply compute the extreme points of your input point sets. And you take that point as an epsilon kernel element, and you return it. Okay? So this only takes near linear time to compute, and your final epsilon kernel is of size independent of n. Okay? So putting this together, we have a very simple algorithm. This is well known to approximate minimal enclosing ball. I first, using what I just described, computing the epsilon kernel in near linear time in this time. Then after that, I simply solve the minimal enclosing ball only over the epsilon kernel point sets in poly time. Okay, so that's it. And it's kind of, I mentioned that the first thing that comes to us is that, okay, can I just then have a neural model kind of simulate this? Okay, and it turned out that there's one challenge, which is that a lot of geometrical algorithm requires argmax. Okay, you really need to compute the argmax. Okay, while in the neural network, we don't have that. We have the soft version. We often use softmax, okay, which is actually fundamentally a little different from argmax, okay? So I have to first address that. And it turned out that this whole epsilon kernel theory can be relaxed to the following concept, which we call the relaxed epsilon kernel, where you no longer require Q to be one of the input points, as long as you just require this Q to be within the convex cell of the input points. Okay. So you don't have to worry about what this is, but anyway, with this relaxed definition, we show that all the theoretical guarantee of epsilon kernel still translates to this relaxed version of the epsilon kernel. Okay, so it still works. And you also have an algorithm to compute this relaxed epsilon kernel. Again, you don't have to read, but it's super simple. And essentially, it boils down that taking some direction, and then you're only using ReLU to limit yourself to within that range, and then do a convex combination of points within that range. Okay? So this turned out to be super simple to be aligned with the sum former. Okay, in particular, our input is set of points. Okay, you only need one block of sum former first mapped from d-dimensional points to some k-dimensional points. Then you do a column-wise L1 normalization. Then you take the inner product of this and the input point set. Okay, so this gives you only a set of points in k-dimensional. This essentially is your epsilon kernel. Okay, so the sum former block, you only need one. It's very easy to simulate this. Of course, in practice, we use more than that. Okay, and you have the guarantee that this simple model indeed can approximate this epsilon kernel algorithm that I just described. Okay, and once you have the epsilon kernel, you can add the MLP at the end to spit out the estimate the minimal enclosing ball. Okay, from the epsilon kernel. So before I show you the final architecture, I want to first show you that this alignment actually do help to improve the performance. So what I'm showing you here is basically, you don't have to use a sum former here. You can also use a transformer here. Okay, and in practice, we didn't use the L1. Originally, we showed the theory using L1 normalization, but turned out the softmax also works. Okay, so empirically, we use softmax. Okay, so here's some here we only evaluate on the epsilon kernel, not yet the minimum enclosing ball. As you can see that this is a sum former version, this is a transformer version. Okay, so you can see that in distribution, their performance is kind of similar. Okay, however, when you go out of distribution, the sum former version is much better than the transformer version. Okay, even though that they theoretically they both have the capacity of implementing this epsilon kernel algorithm. Okay, but this little alignment actually make the sum former followed by this softmax, and then inner product with P, the specific architecture, make it actually works out of distribution also very well. You can also see here in terms of the size. So the bottom one is the sum former. This is the transformer. So they are all trained with about 200, I forgot, up to 500 points, but then tested on up to 5,000 points. Okay, so you can see that the growth is very different. Okay, so which is we did try to train for a much longer time for the transformer as well, just in case that your model is not trained fully, but we see similar behavior. Even if the sum former in the end can drop, still I think this suggests that when you have a little bit of alignment, it's much easier to optimize to train to get a better generalizable solutions. Okay. But that's not yet the final model because we want to solve this problem for this extended measure, like fitting the mean width, annulus, and so on. And the epsilon kernel directly only works for the faithful extended measure, those that with some convex, which themselves are convex. Okay, and a more general approach for the extended measure is through this really beautiful linearization technique. So here's the idea. You give me a set of points that, let's say you want to compute the width of the minimal width annulus that covers all the points. This min width annulus, this is no longer a convex problem, okay, different from the minimal enclosing ball. Okay. So it turns out that for many of those measures, what you can do is that you can first lift the set of points to a set of high-dimensional linear functions suitably. Okay, there exists such a way to lift them to high-dimensional functions. Now, instead of set of points, you've got a bunch of hyperplane higher dimensional space, okay? And your original, this quantity that you are estimating now becomes the so-called smallest extent, like the distance between the upper envelope and the lower envelope of this hyperplane. So now your problem becomes looking for where is the distance between the upper envelope of this hyperplane and the lower envelope smallest, okay? And that itself can be dualized back to, in high-dimensional space, each hyperplane can be dualized to a point, okay? Turned out that can be dualized, go back, become points, but now no longer in the input space, d-dimensional. Now it's a higher dimensional space, and then you use the epsilon kernel to solve it there for the dualized point sets. Okay, so this is a framework, that linearization framework. Okay, so why do I describe this? because this finally suggests our final model. This is a final model, which is for this kind of extended measure. All of this extended measure falls within this framework. Your model is an encoder, processor, decoder framework, where the encoder is basically do that linearization, okay, and also intuitively do the linearization to a higher dimensional latent space, and also dualize them into point sets. And then your processor framework is simply compute that epsilon kernel in that latent dimensional space. And then once you have the epsilon kernel, your decoder then decodes the final quantity that whether it be the radius of minimum enclosing ball or the volume of the compact cell, you get it from the decoder. Okay, so this encoder process decoder is also inspired by one of the earlier work by Peter and co-author in solving a range of graph and other problems. Okay, so the nice thing is that now this whole family, your processor, this computing epsilon kernel, only need to be trained once and can freeze. And when you have new problems coming in, you just need to train the encoder and decoder. You train for the linearization, and you train for how to get the solution back, the decoder. Okay, so the middle one can stay here. The middle one, we're going to use this epsilon kernel approximating neural network to put it there. Okay, and so let me first show that using this model, now if I just do the minimal enclosing ball, remember this is directly if I just use a sum-former or use a transformer in an end-to-end manner, this is the result we got. And then now if we use this new one, this is the result we get. So this outperform the previous direct neural network. This is still pretty simple, the neural network architecture, okay? Now, we also compared this with a classical algorithm, which you first compute the epsilon kernel, and then there's a really beautiful randomized incremental algorithm to solve minimum enclosing ball by Riemann Wessel. And it turned out this is super hard to beat. It's a very beautiful, very simple algorithm. So we are much faster, but our error is actually much worse compared to that classical algorithm. However, if you go to more challenging problem, like the mean width annulus, then we get a similar error, but then we are almost 20 times faster using the neural model. Okay, for the minimum enclosing ball, it's a well-studied, there are very efficient algorithm exist. I think it's very hard to beat the algorithm baseline, but then you want to go to more challenging problems using this. Okay, and this is just to show more comparison with other neural network baselines. Okay, so I think here S stands for that I'm going to use some former in the middle for the epsilon approximating. T is when I use transformer. Okay, the extended frozen means that for this encoder, processor, decoder framework, I trained the middle processor network, neural network, that part, which intuitively is doing the epsilon kernel, and I freeze it. I don't change it anymore. I only train the encoder and decoder for specific tasks. End-to-end means that you just train, you still use this encoder, processor, decoder framework, but you let all the weights to be trained each time, okay? And the baseline, I'm a little confused about this baseline. Let's see, what do I say here? Yeah, so sorry, we're simply using the sum former and the transformer directly end-to-end, okay? So now there's a lot of results here. Let me just summarize some of the key points here. Okay, so as you can see, there's this new framework which is using sum former and phrase this middle processor network. This usually is the best compared to all the other models. Okay, and in general, the sum former version outperform the transformer version, which is also sum former is faster than the transformer. Transformer is more powerful, but for this family of problems, you don't need that power. Okay, so sum former is sufficient, and for the baseline, however, sometimes transformer is better than the sum former, which is interesting because this is also probably because for the baseline, there's no alignment. So just directly using sum former is not good for those problems, and the transformer has a bigger capacity to solve them. Okay, and as I said, that this is just one example. This is one of the recent work that I forgot to say that this was my students, Samantha Chen, Auren Cioli, and also my collaborator, Anastasios Sidiropoulos. Okay? And so this is one example where you can try to, your neural model is still very simple, but then you design it with a little bit of guidance from the algorithm ideas, and then this help you to make the model, at least in very limited setting that we're testing, generalize better than if you just directly using end-to-end neural network. Okay, and I mentioned that there are also some earlier work that we did, including the neural approximation of the largest distance for Euclidean point sets, and also the N. Steiner mixed neural algorithm framework to solving this minimal Steiner tree problem in Euclidean space. So this is an NP-hard problem. Okay, so I'll be happy to tell you more in person, offline, if you're interested. All right, so this this completes what I want to tell you. Let me just summarize that one message that I would really like to make is that out of this, I think in the modern regime of using AI and machine learning, especially in a lot of AI for science applications, I actually think that this out of distribution is very crucial. Okay, and I think this is also partially already observed in practice. For example, if you think about it, that all this grokking behavior that now people start to see more and more often in practice, that is a form of out of distribution, because I mean, you see that at the beginning, your train error and even a validation error can be flat, can be very low for a very, very long time, but then only after very, very long time, suddenly that the test error really drops, which suggests that the train loss and the validation loss themselves may not be a direct measurement of the generalization bound anymore. Okay, so I think this is a issue probably quite important in the modern regime, and the message that the theme that I'm trying to take, which is also following a lot of work, including work by Stephanie, is that sometimes using a little bit algorithm insight combined with machine learning can help you to develop a more principled neural algorithm, or to justify why certain neural network actually works better. Okay, so there's also certain recent work on the in-context learning setting where they suggest that the in-context learning, say for linear regression type of problem, essentially is actually carrying out the gradient descent for a linear regression. That's one reason, potentially, that's why the in-context learning works. Okay, now, in general, this, however, remains very hard, and we also heard from this morning's boot camp, for example, by Thin, that without some assumption, this out of distribution probably will be a hopeless task. Some sort of assumption, or either on your task structure or model structure or the training procedure has to be made. Okay, and here in this talk, I mostly just focus on the architecture alignment with the task structure. I mean, even for my first theoretical justification, I didn't mention the optimization issue, because the results there says that if your loss is sufficiently low, then you have this guarantee. But can I train my model to get using through the standard gradient descent or stochastic gradient descent so that your loss indeed gets so low? That's not clear. Can we guarantee that's not clear? Okay, for the small model case, like the one where our neural network is very small, we have some current work which seems to suggest that you can also show that standard optimization works. But in general, I think it's very, very open. Okay, and another thing that I want to mention is also, so suppose that in the end, it's probably also unlikely that we can have this kind of generalization theory or generalizable module for all possible algorithms. But rather, perhaps what we want is to have maybe for some key algorithm primitives. Okay, and for those very key algorithm primitives, we argue that we have generalizable algorithm procedures. And hopefully that in the future, your neural net, you can have another architecture on top of that, learn how to combine those primitives, those modules, to solve more complex problems. And this would also help us to potentially discover novel algorithms instead of just align with specific known algorithms. Okay, so this collaboration of neural modules, how them can combine with can be combined together to solve harder problems, or when you have the composition of a smaller generalizable module, do we have a theory to argue in what case can we say that the final neural model also have a generalization guarantee? So all of those remain very open. Okay, and another interesting question is that I also think that this algorithm tasks actually provide us a pretty nice platform to probably study generalization behavior, because it's very easy. We know the behavior of algorithms. It's very easy to create a data set because we know how the output should be. Okay, so it would be interesting to use this algorithm as the algorithm tasks as the problem set and try to probe, design ways to probe whether learned model really learned a procedure that generalizes or just fitted the input data, etc. Okay, all right. I think I'll stop here. Thanks for your attention.
Any questions?
Thank you for a very nice talk. I have two follow-up with this kind of the concluding slide. One is, what do you think about the role of the data set? So for example, in the first part of your talk, you showed that just that A graph is important to pin down the system of linear equations, and adding extras doesn't really help, may even hurt. And then the second related follow-up is, you mentioned optimization, and I know that for example, in the transformer literature, when people train these models to solve harder tasks, they usually use curriculum training. So ask the model to solve simpler instances first, and then go up above the hierarchy. Can you mention maybe some ideas of that? Maybe also we can use some sort of that techniques for these graph problems.
Sure. So, so for the first question, the role of data. So in general, I think it's very important. And maybe the first result that I'm showing is a little bit biased, because I think in general, there are multiple factors that involve, like the structure of the data, the structure of the task, the problem at hand, your architecture, and also your training procedure. Okay? And it's a very complex problem, and very often we take some slices, projections. I think in this particular talk, especially theoretical results, I kind of projected into this just the architecture, neural architecture, and the task structure. Okay, and for this particular results, actually, as you can see, the data is very important. Okay, because we have specific graph as the training set. You can use more larger training set as long as you contain that, but then the theoretical guarantee actually what degrades. Okay, so how to integrate all of these different aspects? I think it's non-trivial, but it's a good question. A lot of work on the graph functions, for example, you can think that is on the data side, right? Because you're saying that if the data has this beautiful structure, such that there's a limit, such that the size, there's a certain metric space where the size really doesn't matter anymore under suitable metrics, right? So there are different ways to handle this. I don't yet know how to integrate them together. It's just we're taking different slices looking at this problem. For the second question, I'm not familiar with what you mentioned, but I think that that's in general, that's kind of a little similar to this, having certain primitives, and maybe for smaller problems that you give more guidance, like a curriculum, to train them better, and then hopefully then have some other ways to combine those smaller modules to solve more complex tasks. It's probably along the line that you mentioned, but I'm not familiar with the literature there. Yeah, thanks. Yes?
So you said that out-of-distribution tasks are hopeless unless you introduce some input domain structure into your training neural network or whatever you're using. So, well, how do you explain this? You know, a lot of the machine learning community talks about emergence.
Right. I don't think it's not. So when I say that, so what happened? This is also a question I asked earlier. I think what happens. Nobody understands there's an emergence, and there are a lot of studies into that. But I think there's also training aspect, and I think there are a lot of studies that we have better understanding that the training procedure actually have implicit bias and implicit regularization that's happening. So for example, some of the, Stephanie's probably an expert in this, probably can tell you more, some of the optimization procedure implicitly is doing L1 or L2 regularization, for example. So I think that's probably explains certain cases why we're choosing specific. We're not just going to any optimal solution, especially in the over-parameterized regime, you have infinite number of optimal solution. But it seems that the training procedure is choosing certain specific families of optimal solution. And could be that those solutions are more generalizable due to their minimal description lengths, simplest solution, etc. So
when you're talking about training procedure, do you mean like
gradient descent, the stochastic gradient descent, and so on.
Okay.
Yeah.
What role do you think the reinforcement learning part has in this? Because there's also a lot of conversation on how important the RLS aspect of training is.
Right. So, so that's a little different. I mean, in fact, for a lot of this hard, including combinatorial optimization problems, there are also a lot of work on using reinforcement learning. So for example, some of the earlier work, they use RL to help to learn a better policy to decide if I'm going to have a Brownian bound procedure, to decide when I'm going to have my cutting plane, and so on, to make those decisions. Okay, I would say that this size generalization issue remains there as well. Okay, because over there, I mean, when you have RL, when you train for your policy, you're still taking, say, if I currently have this status, I need to decide what is the next. And this problem size, most likely during the training, you're still using small problem sizes. And when you use it later, you might want to apply this to much larger problem. So this size generalization issue remains there as well.
I have a question, and if it's too much into the details, we can chat offline.
Sure.
But do you have an intuitive, explanation if you take, let's say, 8 random graphs, then you form the system of equations with those one, what goes wrong, and why do you have to use this phrase?
Right. So I think for the small case, I have some better intuition, and I think that if you limit on random graph, I think it most likely would work out. I don't know about the over-parameterized case. And the reason is that those 8 graphs, essentially all we need is that those weights, that you see the graph's topology is very simple. We just need the weights to be well separated. So as long as your random graph, I can choose a sufficiently large set that give me that, I can get some bound. But for the over-parameterized case, I think it's more challenging. And I hope that the random graph would work. I think it would be very interesting if it works. The reason is because that so right now, we're choosing this specific training set because we know the target is this Bellman-Ford, right? So in the future, when you train your model, you may not know what's the task, but you want that through your training set, whatever the target is, you can learn it, right? So if random graph works, then I can just use a random graph as the training set, right, without being task specific. So I think it would be interesting if one can show that, yeah.
Okay, if there are no other questions, then let's